Polyaniline is a conductive polymer that has seen much research. Like most conductive polymers, it is difficult to form into macroscale structures. One method for addressing this difficulty is by electrospinning. Using this technique, long continuous fibers can be formed with diameters as low as 1 micron. Electrospinning requires a viscous solution for fiber formation, and due to its low solubility, it is not possible to achieve the attendant viscosity with polyaniline alone. A copolymer, such as polyethylene oxide, is added to increase the viscosity of the source solution. The drawback of this copolymerization is a reduction in overall conductivity of the resulting fibers due to the presence of non-conducting domains. The goal of this project was to fabricate strips of aligned polyaniline polyethylene oxide fibers. Borrowing a concept previously applied to similarly aligned sheets of carbon nanotubes, these aligned polyaniline fibers would then be twisted into yarns. Theoretically, this would lead to a higher conductivity of the sheet by increasing the contact between disparate polyaniline domains, while also generating a useful structure akin to common metal wires or thread. Hydrochloric acid doped polyaniline was obtained and dedoped using excess sodium hydroxide. The undoped polyaniline was then dissolved with equimolar camphor sulfonic acid, or CSA, in chloroform. An equal weight percent of polyethylene oxide was also dissolved in chloroform, and the two solutions were combined, making a viscous green fluid, as seen here. Doping with CSA gives the polyaniline a higher solubility in chloroform and other solvents, increasing the presence of the conducting polymer in the obtained fibers. Electrospinning from the solution was then attempted using the setup shown here, based on one reported in the literature. There are a number of different techniques used for this procedure. This one was chosen due to its apparent simplicity. Unfortunately, the electrospinning was not performed successfully. While fibers were drawn out by the 1 kilovolt per centimeter electric field, they did not travel to the grounded collector as intended. Instead, they seemed to be randomly attracted to nearly any conductive surface, including the syringe pump housing and the metal table on which the experiment was performed. It's possible that the grounded aluminum foil collector was not at a significantly different potential than the other nearby conductors, preventing its selective attraction of the fiber stream. A next step would have been to connect the collector to a negative voltage, a method consistent with other reports in the literature. Lab time available to perform the experiment ran out before any troubleshooting of this issue could take place, but individual fibers, shown here next to a human hair for scale, were collected and examined. The smaller fiber has an approximate diameter of 40 microns, much larger than the fibers reported in the literature. The source solution was stored overnight in a sealed glass vial before being used, and much of the solvent had vaporized. The increased viscosity of the remaining solution is the likely cause of this disparity. The individual fibers were too small to obtain an accurate measurement of conductivity using a standard multimeter, and there was no time remaining to perform a more complicated 4-probe test typically used for conductivity measurements in micro and nanoscopic structures. However, the presence of conductivity in general was seemingly confirmed using a multimeter when it briefly displayed unstable values for resistance in the megaohms while the probes were applied to the larger fiber. It's still an open question whether the intended polyaniline yarn structure has significantly different properties than similarly electrospun polyaniline sheets. Hopefully future work will be able to provide insight once issues with the electrospinning procedure are resolved. Thanks for watching.